Hi, this is Roger from Kanka Labs, and today we continue our tour on our spreadsheet for magnetic antennas. Now, if we recap what we had what results we had in the first episode, where we want to design a single turn loop antenna for the 10 megahertz frequency with a 50 picofarad tuning capacitor. Well, we had the results to get a real high Q factor. We just have to go first of all to a relatively high diameter of our single turn loop antenna of 2.4 meters. That is simply because we only have one single turn. And second is to counteract the skin effect, we have to go to a very large diameter, at best copper tubing of 20 millimeters, so that in the end we get a Q factor of 1600, at least in the range of that value. So we don't have to care about proximity effect because in a single turn loop without any litz-wire there is neither external nor internal proximity effect. But 2.4 meters diameter is quite large, and that is the reason why we now go over to multi-turn antennas. And we stay at our 10 megahertz frequency, and now we want to see what effects we get if we choose a smaller diameter of our now multi-turn loop. Well, let's just try. And our aim is to get, let's say, a multi-turn loop with a diameter in the range of 50 centimeters or 500 millimeters. So let's see if we put in 500 millimeters. We have 2.42 turns. At such low turns number, we cannot take the rounded value. That is, if we have turns in the range 50 or more, we have to adjust the diameter to get nearly an exact round value. To get the effects I want to show you, let's go a little smaller still. With 400 millimeters we are at 2.77. Now let's go to 300. That's quite handy. So we'll aim at exactly 3 turns, and let's see how we get there with 350 millimeter diameter. That's quite handy and well manageable. And we have 3 turns now, and we'll stay with our 20 millimeter diameter copper tubing, simply because we saw that this gives an optimum value of for the skin effect. But now let's see if we keep all other parameters, what happens due to the proximity effect. And here we of course only have the external proximity effect because we do not use any litz-wire, but you can see the skin resistance is only 0.09 ohms. But if we take into consideration the proximity effect, we already increase the ohmic resistance to 0.5 ohms, and our Q factor goes down to 638, and our bandwidth would be 15.7 kilohertz. So this is still a very good value, but let's try to change one important parameter to see if we can get the proximity effect still lower, down to, let's say, 0.2 ohms or something like that. Now, there is only one free parameter that we have, and that is the distance between the windings that we can vary, and therefore we'll change to paper, and I'll show you some graphs so that you understand the calculations here. So if you've watched some of my videos, you know I'm very bad at drawing any diagrams, but I hope I can explain what I want to tell you with these bad graphics here. Well, I've tried to draw a 3 turns loop antenna, and we have now one parameter left, and that is the length of the winding, which is in our spreadsheet counts from the left end to the right end of the winding. And of course you have to watch out. We have already chosen a diameter of the wire, or of the tubing in our case, of 20 millimeters. So if we have 3 turns and we would choose a length of the winding of 60 millimeters, then the turns would be touching, which means the solenoid, as it looks here, would be compressed so that, different to what I've drawn here, each turn would really touch the next turn. And the spreadsheet warns you if that happens. And we will also later see, of course, even if we do use touching turns with isolated material, let's say enameled copper wire or something like that, or litz-wire, then we have to add a little percentage for the isolation. So in our case, we will just see in a minute, if we have 20 millimeter diameter tubing and 3 turns, the minimum would be slightly less than 60 millimeter for the length of the winding. Why slightly more? Simply because we have to take into account either the insulation or a little air gap or anything to isolate the turns from each other. So what is the basic thing I want to explain here with the length of the winding is just the physical distance between the start of the winding and the end of the winding if you are winding it like a solenoid. So I hope this became clear, and now let's return to our spreadsheet. So by chance here was already the default value was 60 millimeters, and you can see here's a little warning. Winding density eta is 1.05, and 1 would be touching turns, and if the value is greater than 1, increase the winding diameter. That's why here's a little correction factor. The total diameter of our either wire or litz-wire or copper tubing, there is a 5% increase just for the insulation or for a little air gap, whatever. And for the fill factor for litz-wire, we will discuss that later. So our effective diameter, even if we use exactly 20 millimeter copper tubing, our spreadsheet takes a 5% extra here for insulation or for air gap. So we have to go a little bit higher than 60 millimeter. So that would be enough, 0.97 as the winding density, which may never become greater than 1. Let's see if we had any results onto the Q factor. Well, we're now at 1000. So the first calculation was obviously a little bit wrong because here of the correction. But anyway, we're still at 1000. And you could see this little increase in distance between the turns from touching to nearly touching has already given a slighter proximity, a slightly less smaller proximity effect. And now let's simply double the diameter. So we go to a diameter of 130 millimeter. And let's see what happens. Now our proximity effect has gone down so much that it's really hardly larger than the skin effect alone, and we are at a Q factor of 2700. Well, that's an interesting result, because that's where we really want to go. So here you can see that enlarging the distance between the windings has a great effect on proximity effect. Why is it so? Because the proximity effect comes into play when you have neighboring turns, and if you increase the distance between the turns, the detrimental effect becomes simply less, because the single turns are separated by a greater distance. Let's see if it makes sense to increase that still more, which would make our loop a little bit ugly, but let's see if we go to, let's say, 200 millimeter. And yeah, it has gone still a little bit down, but not so much as in the first step. And now let's finally make the winding, let's say, nearly like a cube, so that the length is the same as the diameter, 350 millimeter. So now each turn would be separated from its neighbor by 100 millimeters, or 5 times. As you can see, the inductance also changes, so you have to adjust the diameter a little bit, because the inductance of a solenoid coil, which is nothing else but what a multi-turn loop antenna is, it changes not only with the diameter but also with the distance of the winding. So we have to adjust this a little bit to, now which direction? No, that was wrong. So let's say we're near enough now with a winding diameter of 300 millimeter and the length of the winding of 350 millimeter. Let's see. So now you can see now the determining factor is again the skin resistance. This is 0.12 ohms, and the proximity effect only gives an additional 0.03 ohms, so that in the end we get as the sum of both 0.15. But you can see now the skin effect has already taken over, but we're already at a Q factor of greater than 2000. So what do we learn? Increasing the diameter between the turns reduces our proximity effect, and that's very important and to remember for our next example, where we will determine the parameters for a frame antenna. So we'll now replicate the calculations I've made for the frame antenna you can buy as a kit or readily built from us. And you can see in the background how it looks like. It is the shape is, as you can see, square-like. So we have to get away from the circular shape and go to a square type shape. And because the frame antenna was optimized for the medium wave range, we change our frequency to the middle of the AM medium wave range, 1000 kilohertz, and as a tuning capacitor we take, let's start the calculation a different way. Usually the limiting factor is your tuning capacitor, and a typical value is 500 picofarad. But with that is the full capacity or capacitance of our variable capacitor, and that tunes to the lower end of the medium wave range, which is somewhere in the range of, let's round it to 500 kilohertz. So our necessary inductance is 200 microhenries, and we'll now go back again to 1 megahertz, because this is the higher frequency is more critical, and adjust the tuning capacity for that so that we're back there. That is a good compromise, because that is exactly the value I had in my calculations. So your tuning capacitor is set then to 150 picofarad, although the full capacity is 500 picofarad, just to tune to 1 megahertz. And we need a necessary inductance of, rounded to 170 microhenry. Now we're still winding on air, although our frame antenna is wound on a frame made of acrylic. It touches the acrylic only on a few millimeters, and anyway, acrylic still has a magnetic constant, or the relative permeability, just like air, because simply it's not a magnetic material. So what is the winding diameter? Now our frame antenna has a diagonal of 500 millimeter, and if you multiply this with the square root of 2, we get a winding diameter of 350 millimeters. Of course, our length of the winding now is not, as in the last example, 350. Let's change this to, let's start with 25 millimeters, and let's see where we get from there. Now we have a square shape, and if we start with a 25 millimeter length of the winding, then we get 14 turns, or 14.15, which you can round to 14 turns. But just to give you a better impression of the action of the proximity effect, we will start with a smaller value with, let's say, 15 millimeter, and we are still at nearly 14 turns. And now, because 1 megahertz is the limit where we can use litz-wire, we will now change to litz-wire, and we take exactly what we choose for our frame antenna, 90 strands, and each 0.1 millimeter in diameter. So let's see if we, so now we already get touching turns, because if you have 19 strands, each 0.1 millimeter, your whole bundle of litz-wire is nearly 2 millimeters in diameter, and this does not fit here, so we have to go back to, let's say, 25. Let's go back to 30 millimeter. Then we are here at smaller than a winding density of smaller than 1. Okay, let's see what we get as the DC resistance is 0.471 ohms, and let's see what we get as the skin resistance due to the skin effect with the litz-wire we choose is 0.52 ohms. That is okay. So it's hardly greater than the pure DC resistance. So the litz-wire counteracts the skin effect very well, at least if we choose this combination of number of strands times the diameter of each strand. So we can leave it at that way. You can guess that I've already predetermined the near optimum values for our frame antenna. And now let's see what the proximity effect. Now the external proximity effect has hardly any effect. You can see it only gives an additional 0.15 ohms. So again, for explanation, the external proximity effect is due to the effect, the magnetic effects between each turn. But now we still have the internal proximity resistance between the litz wires. Again, this is experimental. All the formulas above are very well tested. But for the internal proximity effect between the single strands of each litz wire, that is experimental. At least I did not find any exact or nearly exact formulas. But anyway, you can see the effect that we now have a more than 6 times increase in the resistance because we choose litz wire. But let's see at what Q factor we arrive. We arrive at 242, and this is still relatively good for 1 megahertz. You will hardly get in reality any or much better than this. So you can play now around with the, if you want to find a better combination. And you can see now it does not make any sense to try to increase the length of the winding, so simply because the internal proximity effect in the litz wire is the overwhelming effect. And we have a very low DC resistance, a very low resistance due to skin effect, a hardly recognizable increase due to the external proximity effect. But now that we choose litz wire, that limits the Q factor to only, in quote marks, 242. And so you might think, well, if litz wire is the culprit, then why don't we go away from litz wire, just as we did with our single and multi-turn loops, and use thick copper wire or copper tubing? Yeah, good idea. Let's try it. So we go to single solid wire or tubing, and of course now not 0.1 millimeters. Let's just go to 1 millimeter diameter, which is still very well manageable. And let's see what we now get. We get a DC resistance of 0.42 ohms, but because we now only have a single wire and the skin depth is only 66 micrometers, now the skin effect takes over. It gives us 3.34 ohms. Again, the external proximity effect hardly increases the already existing skin effect or the resistance due to the skin effect. And we have no internal proximity effect, so no further increase due to using litz wire, because we don't have litz wire. And we arrive at nearly the same Q factor. So what is the reason why we didn't get any better by getting away with the internal proximity effect, but now we got the skin effect back as the culprit, or as the main error, or the main factor to limit our Q factor. Now what can we do about it? Well, just increase the diameter, as we did in the first episode, when we went also from 1 millimeter to made a big step to 20 millimeters copper tubing. Now 20 millimeters would be a little bit, 14 turns of 20 millimeter thick copper tubing. Let's go in steps. Let's go to the, I would say, to the maximum that we can use here, where you still can bend and manage a solid copper wire. We go to 2 millimeters. Now we have a winding density of 0.98, so the turns are nearly touching, because as you can see, 14 turns times 2 millimeter plus 5% for the insulation already gives nearly touching turns with a 30 millimeter length of winding. But let's just see. Okay, the Q factor has gone down. Why? Skin effect is less, but now the external proximity effect, because the turns are nearly touching, has taken over. Aha! What can we do to counteract this? We again increase the distance between the turns, and we make the length of winding a little bit larger. Let's go to 50 millimeters. Now we get 15 turns. That's okay, 1 turn more, but let's see. Aha! Now, this is until now the highest value. Just by increasing the distance between the turns, or the air gap between the turns, we just got our proximity effect, I think, more than halved. So skin effect is now the same as, so we have 1.76 ohms due to the skin effect, and an additional 1.4 ohms due to the proximity effect, so that we get a total resistance of 3.1 ohms. But anyway, we're now at 340. So that would be the probably the manageable limit with solid copper, and of course we could go to copper tubing, but now we choose smaller copper tubing. Let's say we go to 5 millimeter. Of course we again have to increase our length, otherwise the turns would be touching each other. Let's say we go now to 80 millimeters. And no, the winding density is still above 1. Let's go to 90 millimeters. Okay, that's it. So the air gap between the turns is relatively small, because we are already at a winding density of 0.93, so nearly touching turns. Let's see what we get. Aha, still again a slightly better, but not as much as you might have expected. Why is that? Again, the turns are too narrow to each other. There's not enough space between them. So again, we have the proximity effect, and you can see how you can iterate now to find the perfect winding for your purpose. But now I tell you, your nice frame antenna becomes to look quite ugly if we go to at a diameter of 350 millimeter. If we now go to, let's say 100, let's take the half of that, that is 175 millimeters. So it really starts to look ugly, and believe it or not, when we calculated the parameters for our frame antenna, we also wanted to have a nicely looking frame antenna, so that the ratio between diameter and length, etc., there were good proportions. So this one will really look ugly, but in electronics it's not about ugly or beautiful. Let's see what our numbers say, and wow, now we have reached at a Q factor of 700, so that's really impressive. That's nearly the optimum, because the bandwidth is already so small, that, which I will explain in another video series about crystal radio sets. Your Q factor will again in practice or in reality will halve due to the load you put to your tank circuit. So the bandwidth in reality would be in the range of 3 kilohertz, but that's still you cut off some of the higher frequency audio sound by having such a small bandwidth. But in terms of Q factor, this is the best, probably the best value we can get with a still manageable material. So 700 is really impressive, and these are, let's call it, this is very near to reality, because the formulas here are relatively exact. Only when we come to using litz-wire, the formulas start to, we cannot rely 100%, but you can be relative, because I've tried this really, and I've measured some example coils. The formulas here, you can trust them relatively good. If you find an error, just leave a note in the comments. So anyway, that would be probably the best value we could get, and the bandwidth already starts to become so narrow or so small that if you really want to listen to AM radio stations, the higher frequencies will be cut off. So there is a practical limit not to get too high a Q factor. But anyway, an impressive result, Q factor of 700. The price for that is you have to use 5mm copper tubing. I don't think you can find 5mm solid copper wire that you can still band onto a frame. So copper tubing again is the optimum material. If we have these other parameters, now we even have to, or the formulas say that we had to go to 19 turns and a very large length of the winding compared to the diameter. So the ratio between the winding diameter and the length is 2 to 1. And the next best thing was simply using either 2mm single, something between 1.5 and 2mm solid copper wire, or litz-wire with 90 strands, each 0.1mm. And there we reach at Q factors in the range between 200 and 250, which is already impressive because this is verified by measurements and experiments with our frame antenna. So you can be relatively sure that the calculated results are next to reality. These were the two main examples for multi-turn loops. For either, we started with the 10 megahertz shortwave band and now went to the medium wave range. And just play around a little bit. If you have any questions, put them in the comments. And in the next and probably final episode, I will talk about some special magnetic antennas, and that is loop stick or ferrite rod antennas. and spider web, or what else are they called? Think basket weave or honeycomb coils, which are a little bit different to calculate with this spreadsheet. So I hope you had fun. See you next time. Bye from Roger. Bye from Kanka Labs.